We'll just start at 35 just in case. Can someone just confirm if I'm audible on Zoom? Okay, cool. Okay, cool, we can start. So today's topic is CTC decoding and beam search. Prof has already started about teaching about how CTC is being done, and the bonus part of for you will be the beam search because you have to code it up in the homework 3P1 if you haven't done so. So let's start with the concept of CTC and what's the problem use case we are trying to solve here. So the problem use case we are trying to solve is sequence to sequence modeling, and wherein the input sequence can be of is like input sequence of length n and the output sequence is of length m. So basically the n and m can be different or can be same. Just first let's start with where does the CTC actually fits in the entire picture of what you have already been done. So as soon as you get the input features, you pass it to a prenet. So this is kind of an optional thing to extract out the enhanced features. So you can use CNN or like any other thing which you think which help you get enhanced features out of it. Then you have kind of an encoder thing, which what it does is that it can have RNNs, LSTMs or anything, which will give you out the probability distributions. And finally, the CTC comes at the decoder part. So right now we are learning CTC. In the future lectures, you will go into the different decoders and attention modules as well, which will come in that particular row. And finally, you get the output. So why do we need CTC? So in homework 3P, homework 1P2, we made you solve the problem of sequence classification for phoneme recognition. So if you remember, there was time MFCC features, and for each timestamp, you were calculating the probability distributions. So there, your order synchrony. So everything was available to you. For each timestamp, you knew like the matching between the input and the output sequence. Now here, what is missing here is that we don't have that mapping. We just know the sequence to sequence and the order synchrony. What we mean by order synchrony is that in the you know how the output should look like. Like I ate an apple, so you know that it should be in that sequence, but you don't know at which particular timestamp each and every word should come out. So how can we solve this particular problem? So just to map it with the figures as well, for the homework 1P2, we were trying to solve that kind of problem, wherein we have the input sequence and we were calculating one output. That particularly is an example of it's an RNN right now, it's not a MLP. For MLP, you will have, for each input, you will have an output. You can convert it into an RNN problem that at a particular timestamp, the output you will be predicting, it's dependent on all the previous timestamps of the input till that time. Now to solve the problem of this order synchrony thing, imagine it kind of like we combined all those things together. So it's like the individual RNNs, they are combined together. It's just to make you understand that now these outputs like B, phi, these can be at any particular time. You don't know at what particular time you have to extract out, like you have to predict this particular character. So how to solve this asynchronousness is that we can take advantage of what we learned in like previously, again, homework 1P2, that we can calculate the probability distributions at each and particular timestamp and use that somehow to be able to decode and get out a final output sequence. So how can it be done? As I said, that in the previous thing, we ignored the intermediate time steps, but let's bring them back. let's calculate the probabilities at each and every time step. And what's the simplest way to combine all of this and get the final answer is that we are kind of assuming that in x0, x1, we will get b, and we can just combine all the sequential things. So all triple Bs will be combined and will get predicted as 1B. Similarly for IV, so all the repetitive words will be combined into one character. This has its own problem. We will discuss how can we solve this problem of repetition, but this is the kind of the basic concept which CTC is trying to tackle and help you solve the problem of when mapping is not given. So the current solution which I proposed, they're kind of two things, right? One thing is, so what and how MLP or everything works is that at each time step, you do a softmax and like basically you will get the most probable character at that particular time step. So, and what's our aim is that we want to extract out the most probable sequence, not the character at each particular time step. So if we just keep taking the maximum of the maximum probability character at each time step, it might not be equivalent to getting a maximum probable sequence. Does that make sense? Yeah. So one thing is that, and another thing is that that problem of extended symbols like hello, like HELLO and HELO, you won't be able to distinguish between those two if we just combine the repeated character sequences. The next solution is that we expose external constraints because we know what the sequences should look like. So if we can just impose those constraints on it and predict out and use that to identify what should be the correct sequence. This kinds of indicates to beam search and like sequential greedy search, and we will cover this later. So the overall solution is let's combine both of them. So at each time, the network will output the probability of each output symbol. So if you see below this x0, these are the total vocabulary you have from AH to G, and you are calculating the probability for each and every character in your vocabulary. And also you just mark, so since you know that what all characters is required in your output, you know your output consists of only B, Y, F, only these characters in your vocabulary. Your output vocabulary is just B, Y, F. So you mask out all the other characters. You just don't consider their probabilities. Even if they can be maximum, minimum, whatever their number is, you are not concerned about that. You will just mask them out and just consider the probabilities of the characters of your output vocabulary. Make sense? So firstly, calculate the probability distribution, which will be done with this green. So this green boxes represents your LSTM network or RNN networks. This will calculate the probability distribution. Then you will mask out all those probabilities which are not in your vocabulary, in your output vocabulary. And so finally you will get this kind of graphs like BY, FY. And then you can calculate the probabilities for each and every character. So how does this moves is that you know you will have to start at B. Again, you take advantage of your order synchrony, the knowledge you already have. So you know that your input sequence has to start from B. So you will start from B and you have two options. Either you keep going forward at B or you can move to Y. Why do you have that both the options? Because we are we are trying to find out all the possible extended sequences. So basically, if you have an triple B Y F Y or B triple Y F Y, that will concatenate down to B phi, right? Do I write it down? It's fine. So that's why here we always have two options. Either we move forward or like either we stay at the same character or we move to the next character, just the next one. And this way you will find all the possible paths. Now, but that again, we didn't, we didn't address this issue of repetition, which has also been covered in the last lecture, wherein this again, ROD and ROOD, we won't be able to identify that. Hence, what's the solution of it is that let's introduce blanks in between each and every character. So now your new graph will kind of look like this, wherein you will have these empty symbols And like this can be anything as depending on your problem use case trying to solve. Like in case you have dash as part of your input vocabulary, you will use any other empty symbol. It's just some symbol which is imaginary as not part of your input vocabulary. So this is how you will create your graph now, that from start and end, every time this dash will this empty symbol will be there between each and every character. And now if you see, we are moving, we have got two options or three options. So if you observe properly, either we can move forward again here or to the next one. But for B, you can move forward to the next one or to the third one. You understand why are we able to go to the third one as well? And yeah, if you can someone tell. Yeah, but again, when we were at Y, you just went through forward and just this. Here you can't skip. So this is the condition, this is a check you have to include when you do the coding, that if the next character is equivalent to the previous character, you can't make that skip. And if it's different, then you can have three possible solutions. And this way you are calculating all the possible sequences you can get from this particular probability distributions. This represents your forward pass. So basically this entire thing is your training procedure. So what we do during training, we set up our network, we get many LSTMs and all, we calculate the probability distributions. Then we initialize a separate network based on your output sequence, which has all the characters in that particular order with blank included in between them. We fill that up with the probabilities which we calculated in step 1. Then using your forward and backward algorithm, you will be calculating the probability of the entire sequence. So this will be covered in the lecture, wherein how you use this entire graph to calculate the probability of the entire sequences and all the sequences actually. So there are two algorithms. I'll just give a quick thing, but there are two algorithms, Viterbi and forward and backward. So forward and backward takes into considerations all the sequences, and it uses dynamic programming to be able to calculate all those probabilities of all those sequences in a better and a most efficient way. Viterbi just takes into this assumption that it's dependent only on the parent. So the most probable parent is used to determine what should be the next child. Viterbi, that's why Viterbi is not used, it doesn't give best answers. Hence, forward and backward algorithm is used because it takes into consideration all the sequences. So once we have all those probabilities, this is used to calculate the loss, then backpropagation happens, and all the divergence is being calculated. Yeah.
I'm sorry, can you explain again? When can we not skip?
Okay. So when can you not split? Yeah. So in the scenarios wherein there is like Y and Y, when there is repetition. So this is the repetition you wanted to avoid in your previous scenario. Like you want to know that you have two different Ys. We call it I. Okay, whatever it is. So you want the model to know that there are two I's. If you make a skip, then it will just consider it as I and I. And then you will end up concatenating it. Okay. And so simple, like where did I reach? After forward and backward algorithm, so basically this will help you create, so that's why we call it CTC loss. Because it helps you calculate the loss function using which you will backpropagate through the entire network and update the parameters of the entire network, and it will help you to calculate solve this problem of classification wherein mapping is not given. Now during inference, what we do? During inference, we don't know the order, right? We don't know what's the output order is, what the output order should be. So for that, we use different algorithms like beam search, greedy search, and different thing, which we'll cover. So for inference, we just have this forward output, wherein LSTMs are there, we have the probability distributions. Now we will use this in next thing. So the first and the foremost thing you can think of is greedy search, wherein you just select the most probable timestamp, and like at each timestamp just select the most probable sequence, most probable character at that particular timestamp. it's basically again that problem that overall you can't make sure that the overall sequence is maximum if each character is maximum. So we have another solution which is, but I guess we'll cover. I'll just post the slides on Piazza.
Hey, so yeah, as Shani mentioned, at inference we do not have the outputs, right? So we need to perform. We can use make use of greedy search or beam search, whatever algorithms we have. So greedy search, like as evident in its name, it's basically just taking your. So for example, if these are your outputs, right? These are your Y probabilities, and these are your symbol set. Symbol set is basically your target set. What are the number of characters that you have? And these are the probabilities. Then in that case, what greedy search would do is at each instant, it would just take the maximum probable character and use it as the output. So like when we start with A, like at t equal to 0, we see A, then we see B, A, B. So we get our final decoded string as AB, AB. So that's how like greedy search works, and it's very simple to implement. Like just need to take an argmax at each instant. But as evident, it's pretty basic and it is very short-sighted. It does not consider context at all. So as we like looked into homework 1 part 2, right? Context plays a very big role in all of these things. So we would also like want to consider what happened before instead of just considering what is happening at that particular instant, right? So here is when like this, there can be another way to uh, calculate these values. That can be an exhaustive search. So what the greedy search score, if you look at the values again, this final score of this graded sentence would just be the product at each instant. So it would be just 0.391 times 341,402,358. And that would be the score of this particular decoded string. So another way can be if we perform a very exhaustive search, where at each instant we take all possible characters and we take all possible characters at each instant. So that will, in this case, that might not seem very complex. It would just be like 4 cross 4 to the power 4, because we have 4 instants and we have 4 characters. But as you scale that up, it's very, very computationally exhaustive, and it's not like what we would prefer. It's just a brute way to consider more values, and like it's not like the most ideal way that we would want. So on one hand, we have like greedy search. On the other hand, we have exhaustive search, which like have their own pros and cons. But we would want to lie somewhere in between, right? So that is where your beam search comes in. So what beam search does is, so in greedy search, we were just considering the top one path, whereas in exhaustive search, we were considering all n paths. So what greedy search does is what beam search does is it explores the top k paths, which we define as the beam width. So we have a better decoding strategy than greedy search, and it like because we're considering more paths, but it is still more computationally feasible because we're not exhausting our entire search space. So this is kind of a suboptimal like trade-off that we have, and we can kind of tune our computational expense and our like whatever our greediness expense with the help of this beam width k. So as in when you increase your k from like whatever values you have, you would be able to like move into your you would be able to explore your search space accordingly. So let's see now how beam search actually works. So yeah, we have again we have these same exact y probabilities. We want to find our decoded string. So we have our sequence length as 4. We have like these symbol sets, and we define our beam width as 3 for this use case. So we start at t equal to 0, and we see that like when you're starting, there are no like possible paths, right? So we start with a start token, and we try to explore all possible paths at t equal to 0. So we calculate these scores and we get these scores here. Now is when the beam width comes into play. We have 4 possible paths to diverge at this moment, and we have our beam width as 3. So we take the top 3 scores based on like their probabilities right now, and we now decide that we'll only move forward with these 3 scores. So we go at t equal to 1 now. So we have our old scores from here, from the t equal to 0 instant. Now for each of these best paths, we will explore the all our character spaces. So for example, we have A here and we have a like hyphen which stands for a space. So we have an A here, we have A minus, B minus and C minus. Then we have double A, which like we have a double A, A, B, A, C. And as Ishani mentioned, like these are decoding strategies where a double A is just converted to an A, double B gets converted to a B, double C gets converted to a C. And we'll talk more about that in the lecture. So we have, so and how does our score change now? So our score is just, again, as we calculated in the greedy state, right? It's just the product of all possible, like all of the probabilities that we're taking. So for A minus, it just becomes A 0.391 times 0.257, and B hyphen, it becomes 197,257. And accordingly, we are just like plugging in these scores from these 2 tables that we have. And so for example, for CB, again, we'll have, so CB we'll have 0.271 and 0.341. And we have our new scores now. Again, we'll bring our beam width into the picture. And we see that these 3 are the like highest probabilities. So now we again constrain our search space to these 3 values only, these 3 paths only. And we now take our next step for t equal to 2. Again, like the same procedure follows. We have these existing old paths, we have our new paths coming in, and like the decoding strategies, we have A minus A gets converted to a double A minus B gets converted to a AB. One thing to note here is that the AA doesn't get converted to a single A as it happened here, because we had a space in between. So this comes to be double A, this comes to be A hyphen B, becomes AB, and so on. So again, we calculate our scores based on whatever the values are in the tables here and whatever combination we are making. Now, one thing to notice here is that A minus B and ABB both get decoded as AB and AB. So what happens in this case is that, so when you're writing the code for HW3P1, you'll come across this merge function. What the merge function does is, so for example, you first calculate your possible paths, you take a step. Once you've taken that step, you calculate your new scores. And then when you're going to your next t, like t plus 1, before that, you prune your old paths and you merge them. So pruning is like basically doing this step, and then merging is basically adding the scores wherever the possible paths match. So for example, AB, as you can see, was 0.02 here and like something like 26 here and then 35 here. You add that up, it comes something like 62, which is the sum that we, which is the score that we look into, and not the individual scores here. We look at the summed scores. So yeah, again, as we can see, AB performed the best, and like ABA and ACA like follow it. So any questions? No. Like, yeah, you can stop me if you have any questions. So now that we have our t equal to 2 sorted out, we take another step with our current best paths, and we bring our ABA, we convert it to ABA minus, ACA minus, AB minus, and so on. Now you'll again see that I have, at this instant, like one thing to note is that ABA minus was written as ABA, whereas previously I had not done that. The reason to do that here is the time instant here matches with the end of sequence. So once we're at the end of sequence, we terminate all the terminal blanks. So ABA gets converted to ABA, ABA hyphen gets converted to ABA, ACA hyphen gets converted to ACA, and so on. And again, like some of the other characters also get decoded. AB double A gets converted to ABA, and A double B gets converted to AB. And we again calculate our scores in the exact same fashion, like plugging the values from the tables that we have. We calculate our scores, and now the score under consideration would be the sum of all possible scores. So we can see that ABA gets decoded as ABA in the first and the fourth like rows. So the sum here you can see would be some, and also like in the sixth row, yeah. So the sum here you could see would be something like 20 plus 1838 plus 745, which is close, like which is exactly the same as what we get here. So that is the score that we treat for our further steps and not the individual scores. And accordingly, we have AB here and their sums as well, like 22 plus 9, something like 31. and ACA. So ACA is like 7 plus what, 16. So yeah, it's something like 23. So since this is our terminal like time, since like we are at the end of sequence, we find that ABA was the one that got decoded as our best path here. So if you remember in greedy search, we got something like ABAB, whereas now we are getting something like ABA. So that tells you like how that short-sighted nature is not probably the best in like decoding strategies. So yeah, we have ABA as our final score here, and let's look at like a graphical view of the same thing. So yeah, I think it's visible. The characters inside are visible. So yeah, so we start like it's just like a recap of what we did. We start with our start of sentence. We have some initial like our initial target set, like whatever character symbol set basically. Then we put in our beam width, which like qualifies only these three values, these three tokens for the next step. We take a next step with all possible combinations as evident. Again, we take another step, there are times when we sum the values whenever the values are decoded as the same. And as we move towards the end, we find this end of token. So we just terminate our values and find the total, like what's the best score that we can get. So as you can see, like if you look at this picture from a like wider view, from a zoomed out view, you can see it does look like a beam, right? That is how its name is formed. Like had it been an exhaustive search, we would have seen a lot of crisscrosses and like all possible paths as in a neural network or something, like as in a linear layer. But here, as we can see, it's more like a beam. We are like more focusing on only particular paths and not like exploring everything. So that is basically how your beam search works. And we can also, yeah, so yeah, we start with our decode. So yeah, we have our exact same Y probabilities, and we initialize our values. We have our greedy decoding strategy, which gives us AB as the output, and we have the best path score as 0.019. And once we, so that's our greedy decoding strategy, and we have our beam search decoding strategy as well, which is like I can take you through it again, like just again a quick recap. We start with t equal to 0. We have a blank terminal path which has a score of 0.14, and symbol terminal paths which have scores of like whatever we had in the table, since this is t equal to 0. We take our next step, we append ABC to the blank, and then the current blank paths, current paths with the terminal blank becomes CBA, like blank plus the possible characters and their like their respective scores. And we have like for the other cases that we took, we have ABC going forward. So we have ABC combination with all of ABCs that we have. So those are their respective scores that we calculated. They match with the table as well. And then we take another step. We find that ACA and B and AB were the best performing paths in the like previous step. So we again append like a space to that, and we also append like other possible characters that we have. And again, we calculate these scores. And then at the end, we see that ABA, ACA, and AB qualify for the next step. So we again like append blanks to it, and we append all terminal symbols to it. And we again calculate the paths. We sum them up wherever necessary, like wherever they match after decoding. So we have all of that, and then once we have the t equal to like sequence length, we go to our like we get our final scores, and we find that ABA with a score of 0.046 was the best performing value. So yeah, this like is the same figure again. So yeah, that's how your basically beam search works, and you will be like expected to code this in HW3P1. So yeah, what are your any questions?
How many of you have already coded homework?
Finished or did you say
This beams like okay, then you will appreciate it. because you have to go through the like we have given you an example in the writer.
Yeah.
You have to code the entire algorithm. Because it's in the slides.
Yeah, it's in the slides. If you follow the class, like the lecture
Like,
slides, you should be able to get it through.
4 slides algorithm. So my suggestion is just go through the like mathematical example.
Yeah,
Try to write it down.
yeah, just like see how wherever we are merging things, wherever we are merging things, wherever we are like, how are we calculating, how are we decoding in between, like all of that you can also find in the write-ups and everything. But this is just like free-flowing example that you can use. So yeah, that was all. Yeah, we'll post the slides and the starter notebook.
No, we won't start.
Yeah, like starter notebook we'll redact and then post. We will not post the exact notebook. So yeah, that is that.
Be ready for the quiz as well. You'll have to solve this in quiz.
Yeah, like you'll have some starter, like a very small versions of it should be easy comparatively. But yeah.
I should have said that before, I guess, the recitation. We would have focused more.
I will stop the recording in that case.